Problem 51, page 708. Here we have a solid insulating sphere of radius A equals to 5 centimeter. So we have a sphere. This sphere is uniformly distributed throughout its volume. So it's not a metallic object. In this case, the charge will be distributed inside all the object. So we will get a volume charge distribution. Okay, it's very important to know if you have a metallic or if you have a uniform charge distribution. So the sphere is a uniform object. It's a uniform. In this case, Q equals to 3 microcoulomb and we have a volume charge distribution. In this case, we have to say rho times V. And the radius of this sphere equals to 5 centimeter. Okay. If you want to draw here the sphere, first of all, the sphere with a radius A equals to 5 centimeter. Okay. Second, we have a shell, a conducting spherical shell with inner radius. So we have a conducting. When we say conducting, I mean it's a metallic, okay? We have a metallic spherical shell. When I say metallic, it means we don't have any charge inside. If the charges will be distributed on the outer surface of this shell. But in the case, if we have a charge inside, you will get a new distribution of charge between the internal and the external surface of the shell. Let me write, we have a B, the internal radius equals to 10, and the external radius equal 15 centimeter. It's metallic, so it's not a volume charge distribution. We don't talk about a volume charge distribution, okay? We don't have rho times V. Okay. This shell has Q equals -1 microcoulomb. It's negatively charged. Prepare a graph of the magnitude of the electric field due to this configuration in terms of the radius, the distance between 0 and 25. What I mean, I have to find the magnitude of the field between 0 and 25, and we have to illustrate the magnitude of the field in terms of the distance, because you know the magnitude of the field is not the same inside the sphere, between the sphere and the shell, inside the shell and outside the shell. We have to calculate at each point the value of the field, and at the end we have to do a graph about its magnitude in terms of the distance. Let me first of all draw the graph. So I have to calculate the field first of all, inside the sphere, let's say a point A as a point B at the point C and at the point D, the distance between O and D equals to 25, because I ask you to find R between 0 and 25 centimeter. So first of all, I take in general the case I want to calculate the first case when inside the sphere. It means 1 R, it must be between 0 and A, and small a is a limit. You know, the capital A, the position of A is between 0 and the radius of the sphere. Here I want to calculate the field. Before calculating the field, I want to know and speak a little about the new distribution of charge inside the shell. Okay? Because in general, if we have a shell, let's say here we have a shell, the charge will be distributed on the external surface of the shell. It's a conducting, it's a metallic object. In the case of metallic object, the charges will be outside, will be here. Let's say and if we want to draw, in this case, the field, the lines of the field on the object, we have a negative charge. In this case, the field must be N because it's negative. Okay. Now, let me put a small charge inside the shell. Okay. In this case, I will put a positive small charge inside. We have a small q equals 3 microcoulomb. Here it's a positive. In this case, we will have a new distribution of charge inside the shell, a new one. It will change all the distribution. Look, the positive charge here will attract to the internal surface of the shell the same quantity, but in the opposite charge. We have a positive charge here. Here we will get a negative charge. The value of Qn, the value of Qn on the internal surface equals to minus 3 microcoulomb. So here we get minus 3 microcoulomb. And you know, the total charge of the shell equals to minus 1 microcoulomb, which is equal to Q on the internal. Here we have internal, okay, not internal. Q on the internal surface plus Q to the external surface. On the internal, we have minus 3 microcoulomb plus Q external. We get finally Q external equals to 2 microcoulomb. So here we don't have any positive negative charge on the external surface. It will be changed. So we will get again here a positive charge on the external surface. It will be positive, and the line of the field will be out because it's a positive charge on the external side. You see now, if you have just a shell, or you have a shell with an internal object inside, it's not the same. So here we have a positive, here we have a plus 2 microcoulomb on the external surface, and we have minus 3 microcoulomb on the internal, and inside the sphere we have 3 microcoulomb. We come back to this problem. So here inside we have minus 3 microcoulomb, and here we have plus 2 microcoulomb. And between we don't have any charge. Qn here equals to 0. Q inside, because it's a metallic object. Inside any metallic object, we don't have any charge. Now I know very well the distribution of the charges inside the shell and also inside the sphere. I come back to my problem. As you see here, I write here Q internal of the I am talking about the shell. Q internal, I mean the internal surface, equals to minus 3 microcoulomb. Q external equals to 2 microcoulomb, and Qn inside the shell equals to 0, inside the body of the shell. Now, in general, as we have a sphere, I have to solve this problem by using Gauss's law. As you have a sphere, we have it use a Gaussian surface as we have to select a sphere of radius r as a Gaussian surface. We have to say by symmetric, we select a sphere r, a sphere of radius of radius r as a Gaussian surface, and we have to write the conditions. First of all, E must be parallel to dA, E must be radial, and E must be constant at any point. Now, in general, at any point you want to calculate the field, you have to write the general condition. And also the general condition, the flux in general equals to the integral of a closed surface of Gaussian surface equals to E dA equals to Qn divided by epsilon. Okay, now in general you have to write these conditions. Let's take now, first of all, I want to calculate the field as a point A. A is located between 0 and small a, and the radius A. So we can write 1, R is between A and 0, okay? In this case, we have to choose a sphere. The sphere pass by A. The distance here equals to small r. R must be between 0 and A. The A, I mean the small a, the radius of the sphere. Okay, in general here, the flux equals to E dot dA equals to Qn divided by epsilon. E, we have a positive charge inside the Gaussian surface, so E must be out here. Here we have E out. And also dA is perpendicular to a small portion on the surface. Here we have dA. Okay, so we get the angle between E and dA equal to 0. You have to write here E. We can say E dA cosine 0. It's important to write the angle of cosine equals to Qn divided by epsilon. You know, E is constant at any point on the surface. We can get out E. We have finally EA equals to Qn divided by epsilon. A is the area of Gaussian surface. A of Gaussian surface equals to 4 pi r square. It's here. The area of this one. The area equals to 4 pi r square. And Qn inside this one we have Qn. Let's say Qn, we have a volume charge distribution. Here we have volume charge distribution. So we can say Qn equals to, okay, it's not the same Qn, okay? Let's say small qn. Qn equals to rho times Vn. Here we have Qn here. So we can say here the volume, this one is Vn. Its volume equals to 4 divided by 3 times pi r cube. Okay, we can substitute Qn and A in the equation 1. We get E equals to rho 4 pi r cube divided by 3 epsilon 0 times A is equals to 4 pi r square equals to, we can cancel pi and pi, 4 and 4 r, okay, we get finally rho r divided by 3 epsilon 0. You see here, E and R, we have a linear relation between them. Each time R increases, E will be increased. Okay? So this is the relation between E and R. You can put E in function of Q, because in general, Qn equals to rho times Vn, and also Q, let's say Q of the sphere equals also rho times V. You can substitute, you can put rho equals to Q over V, and you can write the field in terms of Q. Okay. Here we have at the point A, we calculated the field E equal rho R divided by 3 epsilon 0. Let's say the field at the point O, R equal to 0. So the field at the point O equal R times 0 divided by 3 epsilon 0 equals to 0. Let's say I want to calculate, we can say here equals to 0 and equals to A. Okay, so let's say I want to calculate the field as a point here, let's say A prime, which is located at a distance small a from the center. So A, the field as a point A prime equals to rho times R equal A divided by 3 epsilon 0. So if we draw the relation between here, between the field and the distance, I take the distance between 0 and A, okay, from the center to the radius. The relation is linear, okay? We can say like this. Here we have the maximum at this point. The relation between, in this region, let's say, here in this zone, we have E equals to rho R divided by 3 epsilon 0. At this point, I mean at the point A prime, okay? At a distance A, I calculated the field at the point A prime. We have at this point a field, is the same here, a field equals to rho A divided by 3 epsilon 0. And at the center here, we don't have field. So the relation E equal rho R divided by 3 epsilon 0 represents the field at any point between 0 and A, at any point. Now, let me calculate the field between the radius A and B, between the sphere and the shell. Before, you can see here, like we have a sphere here, okay? So, okay, let's say like this. So at the center here, we don't have any field. When we increase the distance, the field will be increased, okay? At this point equal here. Let's say here, okay. The field at this point equals here. The field will increase with the distance. We arrive to the distance A, the radius, we get the maximum value of E equals to rho A divided by 3 epsilon 0. Okay, this is a relation between them. Now we come back to the second part. Here, at B, now at B, I want to calculate the field between B and A. Okay, you know B is between this point and this point, between the radius A and the radius B. Okay, to calculate this, I have to take Gaussian surface at this point. Let's say here we have a Gaussian surface like this, passing at the point B. Okay, at this point, the field, as you have, okay, it's a very important point here. We don't need to use Gaussian surface because the charge inside is a sphere. This sphere can be considered as a point charge, okay? We can say just, we delete this one, we can consider the sphere of radius A as a point charge. You have a video I talked about this point. It's important because you don't have to waste your time to do the calculation. Just you can say any point charge, this object can be considered here as a point charge because you are calculating the field outside the sphere. If you want to calculate the field inside, you have to use Gaussian surface. But outside any spherical shape, you can consider the object as a point charge. As here we have a point charge of Q equals to 3 microcoulomb, and the field at the point B, I take the point B, at the point B, it will be directed outward like this. We have EB, you know, EB as magnitude equals to K, Q inside, we have 3 microcoulomb. Anyway, it must be an absolute value divided by the distance between them square. This is the relation of any electric field between A and B. Okay, at any point here between A and B, EB equals to K times 3 microcoulomb divided by R square. Okay. Okay, let me draw here. I am talking between this point and this point. Okay, the field between these 2 points. Let's say this point A prime, and this point is B prime. So we have I am talking about A prime to B prime, A prime to B prime. At any point between these points, the field equals to KQ divided by R square. And you can calculate, for example, E of the point A prime. You calculated already this value equals to, you can see here, if we get the same value as before, we have K times Q. Here we have Q divided by the distance square at A prime equals to A. Okay, here we have A square. Okay, now we have this value. And before, when we calculated EA prime, we had EA prime equals to rho R divided by 3 epsilon 0. How these values are equals? How can we prove that EA prime equals to A prime? I said you can substitute here rho equals, you know that Q equals to rho times V. So rho equals Q divided by V. You can say here rho equals Q divided by V. V of this sphere equal 4 over 3 times pi r cube divided by 3 epsilon 0. Okay? Equals to Q divided by 4. We can cancel 3 and 3. We get, let's say here, we can say equals, okay, to Q divided by times 3 will be up 3 and down we have 4 times 3 pi epsilon r cube. Okay, Q times 3 divided by 4 3, I think it's okay. Here I forgot, we have R here, okay, times R. Here times R. So 3, and you know 1 divided by 4 pi epsilon equals to K. We can say K Q R divided by R square divided by R square. And A square, A prime is at the distance, in this case, R equal to A. So we can say here KQ divided by A square. You see here, we have the same value. Okay. So it's okay. We have a right answer. Okay. Now, by using this relation, we can calculate the field of the point B prime. You know, E B prime, which is at the distance B, equals to K Q divided by b square. So we can calculate any point between this, between a prime and b prime, any point for a prime, for b and b prime, and any other points exist between this interval. Okay, now it's okay about this one. Let me draw the graph here. You know, to the point A here, we have this point we calculated before, okay? We have this point, and this point is the point at A prime, okay? We have here E equals rho R divided by 3 epsilon 0. And now between this point, here I will use this relation. You know that the field will be inversely proportional to E, to R, and it's a parabolic. So E must be decreased in terms of R. Each time R, okay, E must be decreased. But here, be careful. That the field will be decreased from the point A prime to the point B prime. Here we have point A prime to the point, let's say, point B prime. It's a parabolic. Okay? And you know the field at the point B prime and the field at the point A prime. As the field at the point B prime equals to K Q divided by B prime is at small b, B square, and A prime is at K Q divided by A square. Okay? At any point. Very good. And this zone here is calculated by the relation E equals to K Q divided by R square. What I did for this point, I used the radius small a. For this point, I substitute here the radius small b. And you know, b is bigger than a. So the field at the point B is smaller than the field at the point A prime, because it's inversely proportional to the radius. Okay, now I calculated between O and A prime, and now between A prime and B prime. Now I have to calculate the field between B prime and, let's say here we have C prime. Okay, between let's say inside the shell. Okay, at the point C, I want to calculate the field between B prime, let's say between the position radius B and between the radius C. Okay, now the we apply Gauss's law. The integral of E dA equals to Q N divided by epsilon. What we do here, we have to draw Gaussian surface at this point, passing by point C. Here we can say equals to 0. Why? Because inside the conducting object, we don't have any field and we don't have any charge. Okay? We can say directly because no charge, no field inside a conducting or metallic shell object, any object. So we don't have any charge. We can solve it directly. Okay, now let's draw also the relation between E and R. Between O and A, as we said, is linear. Between A and B is parabolic. Between B and C equals to 0. Okay, we can do like this, 0. Now, between C to the point D, let's say the distance here from O to the point D. Okay, now the point D is here, small d. We have to calculate the field between these points. At the point D, here we have the point D, and we calculate the at D, R is between let me say between C, between greater than C and less than D. D is simply the distance between the center, the radius here. Okay, here we have, no, yes, we can see D, or we can see, okay, we can say D as a point D. Anyway, now to find the field as a point D, also we don't need to apply to use Gauss's law, because at the point D, if you look to the object, you see just a sphere. Okay, it's empty, it's closed, it's not empty, it's full. I don't care. I see only a sphere. In this case, we can consider the object as a point charge. Okay, it's important, this point. What you say here, from point D, we consider the whole object as a point charge because it takes the form of a sphere. Okay, so we can say the total Q equals the summation of the total charge. Here we have -1 of the shell plus 3 charge of the sphere. We get the total charge equals to 2 microcoulomb. Okay, so okay, you have here 2. In general, you can add all the charges inside. We get finally E, the field as a point D, equals to K times the charge Q total divided by the distance square. In this case, we have D square, the distance to the point D. And D can take any position between C and to the infinity. C to the infinity. Now we have E as a point D. We have E as a point C, capital C. We have the field as a point at any position in the space. Let me draw the field in function of the distance. Here we can draw the graph between the center of the sphere and to the infinity. And here the first one is between 0 and A. You see we have a linear relation. Okay. The second one between A and B, the relation is parabolic decreased. Between B and C, we have 0 field. And between C to the infinity, because here we can say R is between, if R is greater than C, R greater than C. If you want to say as a point D, you can say KQ divided by D square at any point between C to the infinity. Okay? Here, as a point C, look here. As a point C and to the infinity, at point C, what we have here, we use this relation. We have E as a point C equals to KQ total divided by C is located at C square. So we have a relation, let's say here, for example, the value of the field, or here maybe, it depends the calculation. We can do the calculation. Here we have the point C with this value, okay? With this value. Here we have the value of EC. And you know, in this region, the relation of E equals to KQ total divided by R square. E is decreased. The relation between E and R is parabolic, decreases with the distance. So the field will decrease to have a value equals to 0 at infinity. Because when R is very large, E equals to 0. Okay? We can draw better. Okay. Here, between this point to the infinity, between this point and this point. Okay. This is the answer and the graphical relation between the field and the distance. I think it's all about this problem. Thank you.